work with Ashwini Vaidya from IIT Delhi and James Evans from University of Chicago, titled "In Her Shoes: Gendered Labeling and Crowdsourced Safety Perceptions Data from India." The context of the study is the proliferation of women's safety mobile phone applications in recent years in India, such as the apps like Safety Pin and Safe City, which crowdsource street safety perceptions and generate safety maps that are then used by policymakers for urban design and by academics for studying female mobility patterns. Internationally, too, crowdsourced safety ratings is gaining popularity, ranging from the reporting of street harassment, police brutality, and general neighborhood safety. Now, these data sets then may be used to train machine learning models for measuring the physical evolution of neighborhoods, estimating their levels of gentrification, and just creating large scale maps of urban safety. To give you some context, here's what an interface looks like for someone providing crowdsourced data in India on one of the popular apps. On the right hand side, you see annotation of a particular location, including the all important annotation of feeling, which is a subjective rating. This is then aggregated, and the app provides safety scores for different locations. This is in the context of India, but such apps do exist in other parts of the world, particularly in the United States. I'm going to go into a quick literature review and talk about why this is important, because there's actually been work showing that there is a perceived risk of street harassment on women's educational choices. And this work actually relies on the metrics from Safety Pin and Safe City. There are a number of sociological factors behind safety perceptions for women, including the idea of eyes on the street. And of course, it matters who owns the devices from which data is crowdsourced. And there is evidence that there is a large digital divide in developing countries like India. Crowdsourcing for public policy is also gaining importance. And we, of course, know that there is this very deep and important literature on algorithmic bias about how algorithms predict differentially for different groups. So far, most of the work or the seminal papers are on race and gender in the US context. And we believe that our work makes an important contribution, not just in the context of safety, crowdsourced safety data, but also in the context of empirical, rigorous work from Global South. Um, so what we do is we have a set of 50 street views that we collect from different parts of Delhi. And in the paper, we talk about how we collect these street views and how we divide them into safe, 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 unsafe, unsafe, safe, and unsafe, unsafe neighborhoods. We would request you to refer to the paper for the methodology, but we at the end have 50 street views that go into our main survey. And then these are responded by participants recruited from an elite engineering institute in Delhi via an institute-wide email. None of the participants, unfortunately, reported as non-binary. So our sample consists of 106 self-reported female and 118 self-reported male respondents. And we have a fully observed matrix of 224 respondents' subjective ratings on those 50 street views. And we also have a number of subsidiary data sets which are detailed in the paper. This is what the interface mainly looks like. A participant is asked to rate how safe a street image looks to them on a Likert scale, going from very unsafe to very safe. Our main research questions are: does the gender mix in crowdsourced safety data affect the downstream predictive ability of machine learning models? We answer this question via simulations. Are there systematic gender differences in safety ratings data? We answer this question via comparison of means t-tests. And are there systematic gender differences in the vocabulary used for describing street safety? And we answer this question using simple text analysis. A simulation design basically consists of varying the proportion of male and female responses that are fully observed and using those to predict on a test set of both male and female respondents via mean squared errors. So here is the main result. The three panels are the mean square error on the test set of all respondents, the mean square error on the test set of just male respondents, and mean squared error on the test set of just female respondents. And the y-axis refers to increasing proportion of male responses, and the x-axis increasing proportion of female responses. I'm going to go straight to the main result, which is the third panel. And here you see the lowest mean squared error corresponds to dark red. And here you see that as the proportion of male and female responses increase, we initially do better on the mean squared error for female respondents on the test set, except we start actually doing much better as you get more female data. And in fact, the highest level of predictive accuracy is observed when we have almost a fully observed training set of female data. And that's here, the deep red area. And the most interesting result is that as you move from this region, where you have about 50% or less of male responses, and as you move to the top right region where you actually have more male responses, you actually notice that the mean squared error for the test respondents actually drops. Therefore, our main result says that at low levels, observing more ratings from either group's gender improves predictions, but observing more female data improves female prediction. Observing more male data can be inefficient and in certain cases lead to actually worse predictions. We contextualize this by looking at just quantitative comparisons. If we just were to plot the distribution of ratings, we've seen it seems to overlap for male and females. But if we only look at those street views where there's a significant gender difference, we find that systematically females tend to rate lower than men. And also an important factor is that the response times for females is significantly higher, implying that perhaps there is higher cognitive load when making subjective safety perceptions, decisions for women. We also contextualize this using text analysis, where we ask respondents to give attributes that justify their ratings. And here we find, interestingly, that both genders employ different vocabularies when describing the least safe images. Women tend to be preoccupied by seclusion, with about 8 of the top 10 attributes being around seclusion. For females, walls is a really important factor. But for males, animals is an important factor. Walls doesn't feature for men in the top 30, and animal doesn't feature for women in the top 30 either. Vocabularies are less gendered when describing the most safe images, but there are gender differences, and we validate these results using simulations on the distribution of words using KL divergence, which is there in detail in the paper. So summarizing, we find that it's important to control for demographic factors even within big data systems. Large volumes of data from males do not help predict better for women. Females likely use different mental models and associated vocabularies. And our main contribution is that we are adding to the literature on safety perceptions, adding to the literature on global south and algorithmic bias, and we suggest that policymakers and researchers avoid blindly using aggregated crowdsourced data. More implications are in the paper, and we say that we suggest that we go beyond the specific context of gender to look at caste, class, race, etc., and the question of citizen engagement and public policy, participatory public policy. We describe some more limitations in the paper and ways of moving forward. And we hope that this leads to greater engagement on questions of algorithmic bias from the global south. Thank you very much.